So we define congruence mod D. We're going to show that congruence mod 3 is actually an equivalence relation. M is in relation with N if and only if 3 divides M minus N is congruence mod 3. This relation is an equivalence relation. Okay. Step by step. Being reflexive. We need to show that for any integer like M is in relation with M. Okay. So we need to show that 3 divides M minus M. But this is obvious since 3 divides 0, because 0 is equal to 3 times 0. It is true. Symmetric. We need to show that for any integers like M and N, if M is in relation with N, then N is also in relation with M. What's the meaning of that? If 3 divides M minus N, it means that there is an integer like K such that M minus N is equal to 3K. Now, just multiply both sides by a negative sign. So, by algebra, N minus M is equal to negative 3K, or N minus M is equal to 3 times negative K, or just let's call it L. So 3 divides N minus M. So N is in relation with M. What about transitivity? Transitive property. For any integers like M, N, and T, if M is in relation with N, and let me write it here. M is in relation with N, and N is in relation with T, then we can conclude that M is in relation with T. I'm going to show this. So if M is in relation with N, it means that 3 divides M minus N. If N is in relation with T, it means that 3 divides N minus T. So it means that there is K sub 1 in Z such that M minus N is 3K1. This guy means that there exists K sub 2 in Z such that N minus T is equal to 3K2. Okay, well, what we can do, we want to show that M and T are connected together. So if you add these two together, add them, you get M minus N plus N minus T equals to 3K1 plus 3K2. So it means that M minus T is equal to 3 times K1 plus K2. This guy is another integer. It means that 3 divides M minus T, or M is related to T, so it is true. I just showed that congruence mod 3 is an equivalence relation. Okay, now I expect you to ask, how do you analyze the equivalence classes? What's the classes look like? that we showed that they have an equivalence relation, we're interested in knowing what's the behavior of equivalence classes. Now that we have equivalence relation, we want to analyze the equivalence classes. Okay, remember how we defined the equivalence class of, for example, A. This is the set of all elements in the set A such that X is in relation with A. So the equivalence class of an element like A is equal to all the set of all integers such that X is in relation with A. X is in relation with A, or it's the set of all integers such that 3 divides X minus A. But how did we define divisibility? This is the set of all integers such that X minus A is equal to 3K. K is an integer, but this guy can be written as the set of all integers such that X is equal to A plus 3K, and K is an integer. This is how we define this divisibility. Just going back to the definition of divisibility. So, for example, suppose I want to know what is, for example, for practice, we want to know what is the equivalence class of 0. Based on the definition, it's going to be all integers, the set of all integers, such that X is equal to 0 plus 3K for some integers K. It means that I'm looking at all multiples of 3. So here I have 0 plus minus 3 plus minus 6 plus minus 9 and so on. What are the equivalence class of 1? This guy is equal to all integers such that X is equal to, here you have 1 plus 3K. K is an integer. So, for example, if you plug in 0, you get 1. If you plug in 1, you get 4. If you plug in -1, you get -2. If you plug in 2, you get 7. If you plug in -2, you get -5, and so on. For practice, what's the equivalence class of 2? It's going to be all integers such that X is equal to 2 plus 3K. K is an integer for some integers here. If K is equal to 0, you get 2. K is equal to 1, you get 5. K equals to -1, you get -1. If K is equal to 2, you get 8, -2, -6, and so on. What if you want to form the equivalence class of 3? Take a look at this here. Guys, they're going to repeat themselves. It's going to be all integers such that X is equal to 3 plus 3K for some integers K. Well, it means that I have 3. If K is equal to 1, I get 6. K is equal to 0. I get 3, K is equal to -1, I get 0, and it's going to repeat the first set. These two sets are the same. So equivalence class of 0 is the same as equivalence class of 3. it also equals to equivalence class of -3. You can check that. It also equal to equivalence class of 6. It also equals to equivalence class of -6, and so on. If you form equivalence class of 4, it's going to be all integers such that x is 4 plus 3k for some integers like z. But this guy is going to be the same as equivalence class of 1. Why is that? Because you can write this way. All x values, all integers, such that x is equal to, you can break 4 into the sum of 3 plus 1. 3 plus 1 plus 3k, or 1 plus 3, 1 plus k for some integers, am I right? So it's going to be the same as equivalence class of 1. So if you check this, equivalence class of 1 is equal to equivalence class of 4, which is equal to equivalence class of -2, which is equal to equivalence class of 7, equivalence class of -5, and so on. You can continue this process. You can check that the equivalence class of 2 is the same as equivalence class of 5. You can eventually divide this up into the following scenarios. So equivalence class of 2 is the same as equivalence class of 5, which is the same as equivalence class of -1, equivalence class of 8, and then equivalence class of -4, and the rest of them. So dividing by 3, then you have the difference between two numbers, you're going to get 3 partitions for the integers. So if you look at the integer word, module 3, the congruence module 3 gives you 3 partitions. The first partition, the second partition, and the third partition. The first partition is going to be just x equals to 3k's. The second partition, x is 3k plus 1, and the third partition is 3k plus 2. So we found 3 partitions for the integers using congruence mod 4. You can continue this, you can form congruence mod 2, congruence mod 4, congruence mod 5, and the rest of them.